Okay, so I've passed out here, or I'm passing out a...
Sir?
Well, I'll just turn this off for a minute, David, while I do the lottery here.
I can put you on mute.
Okay. Very good.
So, why don't you guys each come and grab one of those, and that's a random presentation slot.
That's a lot of pressure.
Okay, I can put them on mute too.
I like the first draft.
So I've made a list of groups for the presentation dates for your oral term paper presentations, and it's on this sheet here. Now there's one group that I've classified as biological on the back here, and those 5 presentations are going to be on Thursday, November the 29th. And they're going to share time with some presentations on that date from Utah State University. So that date is already fixed. And then there's 4 groups of 8, and those are going to present on the dates that I've given at the top here, Tuesday, November the 13th, 15th, November the 27th, and December the 4th. Okay, so we need a volunteer from group 1 here. Okay, Leah, yes, Leah, you can do it, Leah. Okay, I need to randomize these things first. Okay, so randomizing. Okay, there you go. Deep breath. Okay.
Oh my God. November 27th.
Tuesday, November the 27th. Okay, so let me mark that one down. Okay, so group number 1, Tuesday, November the 27th. Okay, here we go. We are looking for a volunteer from group number 2. A volunteer. Okay, here we go. What you got here?
Tuesday, November 13th.
Okay, you win. You win. So group number 2. So you're going to be so great and so intimidating that the other groups are going to know that that's the best. Okay, so we've got 2 left. This environmental group. Do we have a volunteer from the environmental group? Okay. Take it away, Clint. We've got 2 choices left. You can do it, man. Okay.
Thursday, November 15th.
Oh, okay. So, Thursday, November 15th. So that means that the last group gets, ta-da, Tuesday, December the 4th. So, and the last group's got several different subjects in it. I had to sort of mix things up a bit just to make 8 presentations. So let me just make it clear again. The first group is on Tuesday, November the 27th. That's entitled Flooding. The second is on Thursday, November the 13th. Sorry, Tuesday, November the 13th. That's Water Resources. The third group, Environmental, is on Thursday, November 15th. And the last group is Tuesday, December the 4th. So for the first group, which is 3 weeks out from today, don't get in a panic like, oh my gosh, I've got not enough time and that kind of thing. I've been through this, every year we've had this same situation. So the key point is to be able to frame your project and to be able to present the general goal that you're getting to. And it's okay to say, I haven't got everything done. I've done these things and I've still got this to do. And it's okay. Frankly, I've looked at these things many times now, and I don't see that much difference between the presentations that are made at the beginning than the ones that are made later. It's even though it may seem like you've got lots more time if you do it later, and you do, the basic idea of the presentation is already there, and so it doesn't change that much actually. So each of you is presenting on your own subjects, and this is our turn to learn from you and your turn to be a teacher and to teach us about what you know well and how the technology is helping you to understand better whatever subject it is that's of interest to you. We'll go through a little bit before the presentations begin on how to put together an effective presentation, but just in a short sense I would say, remember that what people will get is not what they hear, it's what they see. So we've got the capacity in our eyes for really rapidly discriminating lots of images. That's our life depends on it. You've got to react quickly. That's how people get information. When you've got your slides all prepared and you've got lots of nice images in them, that's great. Don't have lots of words. Words are boring. And people go, they just tune out. And also, it doesn't matter that much what you say. It's what you show, what people see. That's what counts. So once you've got your slides together, that's your presentation is largely done. You're just going to get up and you're going to give a commentary, and it's okay. But you're not standing here making a speech with some pictures behind it. No. Your images are what people are going to think about when you talk, and you're simply going to add a little bit to that presentation. Okay, is there any questions about that? Yes.
How much time?
You'll have 9 minutes. Yep. And there's 8 presentations per lesson. That's 8 9s are 72. We have a 75-minute lesson, and I'll be tough on that. So if you're not done, you're going to get the hook. So you'll have 9 minutes. And that includes questions too. So you leave yourself like 8 minutes for a presentation and 1 minute for questions, something like that. And you may think, well, gosh, how can I make my point in 8 minutes? When you go to the American Geophysical Union, you can travel to a whole conference and you get 10 minutes to talk. That's it. You've got to be in and out in 10 minutes, even though you're traveling to a long distance in a faraway place to do your presentation. Oops. Okay, so we are good here. David, are you there?
Yes, we're good to go. So I've just got on the screen here. I guess I should switch the camera to show me.
Okay.
So I've got on the screen. I've got on the screen here the schedule, and we just did a lottery here. So we've got 7 students presenting on the 20th, and 2 presenting with the 5 of yours on the 29th. So we're all set. And it was good to hear the insights about presenting, and now we'll see how many words are on any of the slides that I've got. So we're going to be talking about using digital elevation models, which you've used quite a lot for doing things like mapping stream networks, calculating slope and the like, for calculating height above the nearest drainage or hand, and using that for flood inundation mapping. So this is really a new capability that we've sort of developed over the last few years, and we'll see where it goes. You've seen the basic concept introduced already with the National Water Model and flood inundation, and we're going to get into some of the nitty-gritty details today. And this is work with some of Dr. Maidment and his students. So Jing Zheng is the PhD student there, now a postdoc who's done a lot of this, and then Yan Liu and Xiaowen Wang were NTSA, University of Illinois, doing some of the high-performance computing aspects of it. So I'm just going to give an overview of what is going to come, then talk about calculating hand from a digital elevation model, using it to map flood inundation, using it to then determine reach hydraulic properties, and then some of the further considerations involved in that. And I guess I'll point out that I'll be doing an exercise on this on Thursday, presenting from Texas. So you guys will sort of be on remote control in the classroom here. Scott is going to get the connection set up, and I'll be in Texas. The basic idea is that flooding occurs when the water depth is greater than the height above the stream, or the height above the nearest drainage. So you can think of, you've got some building mapped perhaps by an address point, that is a certain height above the stream. If the flood depth gets higher than that, then that building gets flooded. So it's a fairly simple concept, and you can also figure out the depth by the flood depth minus the height the ground is above the stream bed. So this idea is going to be then used to determine flood risks by basically seeing how deep the water's getting, and seeing how, once you've calculated the depth, how it extends out over the watershed. So I don't know what happened to my title there. I guess it was animated in. We've already seen this. The National Water Model predicts discharge across the continental US. So the challenge is to go from these discharge predictions to the area that's inundated, and this approach is doing that. So the general idea, and I think this might also be a slide that we've seen before, is you start with a discharge, take a National Water Model forecast, you transform that into depth through a rating curve. A rating curve is a function that really just relates the depth of flow in a stream to its discharge. You might also use a hydraulic model such as GISWR for that. Then once you've got the depth, you can create a flood inundation map using hand. Because if you've got the depth in a certain stream and you know that a grid cell is less than that height above the stream, then that grid cell is going to get flooded. And then you can go into the impact assessment. You look at where's the area that's flooded, what infrastructure is in there, what houses are there, and those are the ones that you have to worry about. So those are the sort of 4 parts to that, and the flood emergency response depends on quantifying impact. And it's not only whether it gets flooded, it's also to some extent depth. If the water's shallow, then you would sort of have perhaps lesser damage and people would only get their feet wet. If the water's deep, they're going to get washed away and lives are going to be at risk. So you have to worry about the depth as well. In terms of implementing this with concepts from GIS, we've been working a lot with things like the National Hydrography Dataset and the whole structure of a hydrologic model that deals with streams and catchments. So the idea is that each stream reach has a discharge, and I've got depicted here streams and associated catchments, the catchment being the area that drains to each stream reach separately. Each stream reach then has a water depth calculated from that discharge. So this is a reach-based calculation. The smallest elements that we're working with are reaches. We might make the reaches short or long, but it's basically a reach, and the catchment draining to it is our discretization of the landscape, the tessellation of the landscape that we spoke about in earlier lectures. Then each stream reach has a unique identifier. So we're using unique identifiers throughout to effectively map the association of reaches and catchments. Each catchment has a unique identifier for the reach to which it drains. And then each grid cell has the identifier of the catchment it's in, which effectively provides the identifier of the reach it drains to. And the grid cell has its height above the nearest drainage that's been calculated. So with all of this information that's effectively assembled through calculating height above the nearest drainage, as well as through calculating stream reaches, catchments that they drain to, and the appropriate associations, we can evaluate inundation using some fairly simple rules. If the depth of the water for the catchment with that identifier is greater than the height above the drainage for that catchment identifier, the inundation depth is the depth of the water minus the height you are above the drainage. Otherwise, the inundation depth is 0. So you're high and dry. So the general idea is you've got the streams, you've got the calculation of the height above the streams, you've got the catchments that tell you which stream each grid cell drains to. You've got the flood depths for each uniquely identified stream with some sort of common identifier. ComID here is part of the National Hydrography Dataset Plus, you can combine those to effectively make a map of the grid cells that are inundated and how deep the water is. So the information model that's really involved here is, and this is a slide that came from a recent presentation by Jing Zheng that Dr. Maidman sent me, is you've got the National Water Model forecast for a particular stream. You've got the NHD plus flow lines and catchments, each river segment with a unique identifier. Then you've got all the river geometry information, so the sort of cross-section, the rating curve, and you've got maps of things like height above nearest drainage, the HECRAS hydraulic models perhaps that give you how deep the water is for different discharges, and perhaps you're using LiDAR to get high-resolution information on the topography. And with that information all combined, you can get a mapping of real-time inundation extent. So that's the sort of idea that's behind this approach. And the sort of thing that you get is for a particular catchment. Here I've labeled the depths of the water in each of the reaches, and then the mapped extent of flooding for each of them. I've also indicated here, maybe this is too many words for the slide. This is approximate because it neglects many details of the river hydraulics. The way water moves down rivers is actually quite complicated, and those of you who studied hydraulics will have learned about the San Venant equations and other equations involved in open channel flow, and you can extend them out into shallow water equations for multiple dimensions. It'd be really great to use all of those things, but often you don't have the information. You don't really have the geometry. You may not have the roughness information that you need. So without that information, this hand approach is really a simple alternative that we're evaluating how far we can push it in terms of getting sort of useful screening, quick real-time flood information that can be used sort of for flood mapping and perhaps emergency management. It's premised on how good the digital elevation data is. I mean, if our digital elevation data is poor, or if we've done poor processing of it, then we're not going to get good results. So that's why we're going to be actually paying quite a lot of attention to the details of how we do the digital elevation model work. So here's a video that Jing prepared that kind of goes through the picture. So let's see if this works here. So I think it's showing, this is Onion Creek, which is a river watershed near Austin, and you can see as you go along the discharge increases, and they're counting how many address points are flooded. And on the left you can see around this reach how the flooded area expands and contracts. I've been investigating what to do about the exercise next class, and we're going to be working with Onion Creek, and we might even be able to hone in on this area, or you could certainly hone in on this area and see what's going on in your work. I thought about doing the Llano, which is where we saw the floods a couple of classes back, but when we looked at it, it's huge. It's much bigger than Onion Creek, and I didn't want to get sort of bogged down with digital elevation model processing over large areas, and so we're keeping the exercise a little bit more focused and doing Onion Creek. So let's get on to now calculating hand. Okay, go ahead, there's a question here.
I was just wondering how many cross-sections along your reach are you considering?
So the question was how many cross-sections are we considering along the reach? And the answer is actually none. We're not thinking of the reach in terms of cross-sections. We're thinking of the reach in terms of a single unit where we're calculating reach averaged hydraulic properties. So I'll talk about that later. I guess I didn't have a slide here, but I think Dr. Maidman showed one earlier where there was set of slides where he looked at cross sections, and the effort to try and put together cross sections for a stream network can get quite complicated, and we're trying to effectively develop this as an alternative reach-based approach that is simpler than working with cross sections.
Yeah, well, let me just add a little bit to that, David. So, describing channel geometries by cross sections has been, and in a sense still is, the traditional way of doing this. So, and that's because that's the way it was always done with land surveying. And people did transects with land surveying, and it's fine if you want to do one river at a time when you're doing that. What becomes the problem is when you've got not just one river but a whole network, because what happens is big rivers have big cross sections because the water spreads out a lot, and little rivers have smaller ones, and they all cross over each other, and then some are missing, and you end up with just spaghetti. I mean, there's been a tremendous amount of work that's been put into developing river cross sections, and one of the goals that I had at one time was to get all of these cross sections. For example, the City of Boston has a model library for hydraulic models for the city, and it has 66 models in it. 66 models. That's for individual reaches of the City of Boston. At some point or other, somebody made a model with cross sections. But if you put all 66 models in, what do you get? You get spaghetti, because the people who did it all did it at different times, and the assumptions were different, and the cross sections cross over each other, and so on. So when we started off on this work with hand, one of the sort of innate requirements of this was that we're not just dealing with one river, we're dealing with the whole network, and therefore we need a different approach that approaches the problem at a landscape level and proposes a network-wide result, network-wide solution, and not just a solution for one river. And that's one reason that we're not using cross-sections. And also because we're using GIS, cross-sections cut the land vertically, but there's no reason why we have to cut the land vertically. We can cut the land like this. And that's what we end up doing. We end up saying, okay, we're now going to slice along the river and figure out what the depth of water is underneath it, instead of going chomp, 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 chomp like this. And when you think about that, the advantage of doing it along the river is that you're taking into account all of the geometry of the river as it goes right down. If you do a cross-section, you know lots of detail at this point, actually more than you really need. And then you don't do anything for 500 feet, then you know a lot more detail. And then you don't do anything, and then you know a lot more detail. So in my opinion, this is the way that we're doing this is a better way of being able to describe channel geometries, given that we now have these incredible, the detailed descriptions of just where the rivers are. In Texas, for example, in this year and next year, 180,000 square miles of new terrain data is going to be released. And that's 2/3 of the area of our state. The total area of Texas is about 270,000 square kilometres. But that's about $40 million has been invested in that. And so the question is, now with $40 million, presumably we're getting a better result. And how are we going to get a better result? How do you translate that investment into something that can be used to benefit our whole state? And this is an attempt to do that, to be able to say, okay, if we can develop a process like this, and then we can just systematically apply this over this 180,000 square miles, then we have a better result for our whole state and not just doing one river at a time.
Okay, there's a follow-up. Go ahead.
As far as I understood, you use one rating curve for the whole ridge, yeah?
Yes, that's right.
Yeah. I was wondering to know which session relates to that rating curve. Probably it should associate with the most critical cross-section. Now, if you didn't consider this into your calculation, it's possible that, for example, you get a rating curve for a much, let's say, deeper part of the deeper cross-section of the ridge, and whenever when the flood coming, you underestimate the inundation and floodplain area. And I just wanted to notice that it's important that the cross-section, that we extract the rating curve from that.
Yeah, that's a good question. So perhaps I can prepare something to talk about this a little bit more next time, David, but we've looked into this carefully. And the conclusion that we've reached is that for looking at rivers, it's not one cross-section that matters, because what happens is that the hydraulics of the river actually, the whole river makes itself felt on all of the water. It's not like at one location there's this critical thing that controls everything in most cases. And so what we found is that, in fact, if you look at a rating curve that's derived from one cross-section, and then you take another cross-section a bit further down and look at another rating curve derived there, they're quite different because the cross-sections across rivers actually change quite a bit from one location to the next. So if you associate a rating curve with a single cross-section, what it ends up being is like unrepresentative of what's happening even a short distance away. And so what we've done is we've studied this in detail by looking at the results of hydraulic modelling, and what we've found is that for a river, it takes a certain length of river, perhaps a mile or so, before you've got enough of the river making itself felt on the cross-section as a whole, making itself felt on the water as a whole, that you get a consistent relationship between the depth and the flow. And it was something of a surprise to me to find that out, but what we found is if we look at HEC-RAS cross-sections at successive distances, even short distances apart, is that the rating curves just, they go left and right. It's quite, they're quite different from one another, and it's only over a certain averaging length that you find something that stabilizes.
Okay, thank you. So let me get back to me. So yeah, and I think that that averaging length is going to vary with rivers. With large rivers, it's like the ones they have in Texas, it's probably a mile. For some of the smaller ones here, it's probably quite a bit shorter. Mm-hmm. What I've got on the slide here is the slide you've seen before in terms of the D-infinity model for how we represent flow across the topography, where if, say, we're starting from this grid cell labeled D-infinity, and you are modeling flow as moving perpendicular to the contours, you've got a question, what is the height of this grid cell above the stream, and should I go down sort of perpendicular to the contours and measure the elevation of the stream here, or should I go along here, say following a D8 direction, and measure the elevation of the stream there? And depending on which approach you do, you're going to get a different answer. So basically we've adapted this D-infinity approach to start from every grid cell on the stream. The grid cells on the stream by definition have the height above the stream as 0, and then work back, effectively averaging across the proportioning of flow from each grid cell to up to 2 of the neighbors, recognizing the proportioning is done based on the angle proportion. So if the flow direction on this triangular facet is this angle, say alpha 1, and there's alpha 2, you can calculate those proportions. So TAUDEM actually built in this capability for calculating distance to streams, and the height above the stream is effectively just the distance measured in a vertical sense, and you can calculate distance in a horizontal or a vertical sense. So one of the things that we've done is we've used this D-infinity approach, and I think that's actually got a benefit to it, because it means that the height of this grid cell is not just to one downstream grid cell, but it's averaged over a little bit of a reach of them. So it allows the depths that we're modeling with hands to have a smoothness to them, whereas if you just use D8, you'd get a sort of a discrete roughness to it that would not be that physically realistic. This is the idea here, using the TAUDEM D-infinity vertical distance down function. You've got the point of interest, and this paper with a former student of mine, Teklu Tesfa, we worked out a whole lot of proximity measures that you could calculate from a digital elevation model, things like the horizontal distance to the stream, the vertical distance to the stream, the horizontal distance to the ridge, the vertical distance upstream to the ridge. And it turned out that this vertical distance to the stream averaged over these directions is what we're using in calculations of hand. The way it's done is following a similar approach to what we were doing with calculating of contributing area and thinking of the individual grid cells involved. First, you set the height, and this is height above the stream, to be 0 for grid cells on streams. And then you go to any grid cell off the stream and you say its height is the height from that grid cell I to k, and then the sum of the results proportion based on the flow directions at that grid cell k. And the distance function is the elevation difference between I and the downstream cell k when you're doing the calculation of vertical drop sense. So this became a rule, an algebraic rule we could build into the sort of generalized flow accumulation or flow algebra function I spoke about earlier when we were introducing the D infinity model. So let me go through an example to sort of try and make it concrete. We've set the height equal to 0 along the stream. So here we've got all these orange zeros here. We mark the remaining grid cells as ready to be calculated if all the down results are available, and not ready if the down results are not yet computed. So if I'm looking at this little grid here, all of the grid cells next to the streams would be marked as ready and put on a queue. The ones way up on the hillside will be marked as not ready because their downsleep result is not computed yet. Then for a ready cell, and you can actually let the computer now work in parallel, you can have different processes work on different ready cells, picking them off the queue. So for any ready cell, find its flow direction and the elevation difference to the two cells. So here we've got an example where I've said that sort of these three red cells here are here. The elevation values are given by Z, 435.56, 435.35, 436.48. The D infinity flow direction angle is calculated as 1.3 radians or 75 degrees. So based on those, we get the proportion that's going in the direction of grid cell 2 is 0.33. The proportion that's going in the direction of grid cell 3 is 0.67. So those two proportions, 1/3 and 2/3, basically add up to 1. And you can calculate the two elevation differences. Delta 3 is the difference between this Z value and that Z value. Delta 2 over here is the difference between this Z value and that Z value here. And then we say the height that this grid cell is above the stream is the weighted average of those differences. The 0.67 times 0.92 plus 0.33 times 1.13. So basically we're getting that this grid cell is 1.13 meters above the diagonal one, 0.7 or 0.92 above the straight one. So on average it would be, on a weighted average it would be 0.99. So we would get the hand value for this grid cell would be 0.99. So that sounds like a long, very wordy way to do it. Maybe there's too many words on the slide. It happens in an instant in the computer. And then you can step further back. So once you've got the 0.99 calculated, the 0.95 calculated, perhaps these other ones calculated, you do the same things. Evaluate the up cells as soon as they become ready, or realistically you put them on the queue, and the computer just keeps cranking, picking numbers off the queue, and when there's nothing more on the queue, then it knows it's done. So you can end up getting this value is again the 0.4, the two proportions in this case are 0.4 and 0.6. There's elevation differences of, I guess, 2.74 and 2.1, which when you then add to the heights, those grid cells are above the stream of 1.88 and 2.64, you get this result, 4.88. So there's some of the Gory details. And at the end, you end up with a pattern like this. So previously you had elevation values Z at each grid cell that would effectively correspond to the contours. But now you end up with the hand layer, or some people will refer to it as the hand digital elevation model, because it's effectively a stream normalized digital elevation model that has in each grid cell the average height following the flow directions that this grid cell is above the stream. Now there has been a little bit of discussion as to, well, should we be following flow directions to calculate this height, or maybe we should just go in a sort of straight line Euclidean sense, or should we use D8 or D infinity flow directions? And I think there's still a little bit of evaluation to be done to sort of really figure out what the best approach is. My particular take on it is that the D infinity surface looks quite smooth, and that any sort of differences between some of these sort of subtle method choices are going to be a whole lot smaller than doing this overall. So it's sort of going to be a second order effect rather than a first order effect.
I have a question.
Okay, so there was a question.
So you assume the stream itself has a zero slope all the way, because the stream itself.
So there was a question, do we assume the stream has a zero slope? We're not actually saying anything about the slope of the stream. We're just calculating the height of each grid cell above the point on the stream, or that set of points to which, with the D infinity spreading out, it drains to. The stream could be steep or flat, and we actually need to calculate the slopes of the streams later on when we are doing the rating curve, but we're not assuming we're not assuming anything about the slope of the stream. We're just calculating the height above the point where the terrain enters the stream.
Okay, because the left cell has a higher elevation than the right cell, or yeah.
Right. So in this case, this
zero and zero for both.
well, that's because these are the streams. So these are not slope values. These are height above stream values. And on the stream, the height above the stream is zero. In this case, the stream, we can figure out, must be going from left to right because it's downhill 436.4, 4.01, 5.56, and so on. Any other questions while we are on this? Okay. So this is what you get if you then apply it over a digital elevation model. This is Onion Creek that we'll be using for the example next class, and it's motivated by the flood that occurred close to Halloween a few years ago, and that sort of got us started with some of this work. So now let's look at the mapping of the inundation. The previous one I was focusing on here was just.
Go back to that map, just to the previous slide, just to give you a sense of the dimensions here. The area of this watershed is as big as the area of Austin itself, and the Austin is in the downstream portion of this. And so what happened was actually there's been several floods in this watershed, but there's one in 2013 where there was a big rain at the top end. It happened about midnight, and all the emergency response people came out. The flood went down in the city. They went home again. Everybody stood down, and then about 5 o'clock in the morning, the 911 call started from the bottom end of this watershed, and by about 6:30 in the morning, there was water in 500 houses, and 5 people drowned, and they had almost no warning at all. And so the water came into the city from far away, out in Western Traverse County and in Hayes County, and it came in the darkness. And so being able to have automated systems that will provide a warning of that, and I talked to a lady who, she was in her house and suddenly her neighbour's banging on the door and the water's already coming into the house, and it was still dark, and I mean it was a crazy, crazy situation. I have a friend who was running the rescue response for this, and he was calling for a map to be made of the kind that you'll be developing in this class while the water was going through the houses, actually. So he was getting a GIS person to, hey, how big is the problem I'm facing here? And one of our staff people in the civil engineering department lived in this area, and she was trying to get help from another staff person who's living in our department when her fridge floated past her in her kitchen, and she just freaked out. I mean, these things all happened, and they happened in this area. And so This is one of the reasons why we've chosen this particular watershed as for our study in this class.
And making those remarks and from a GIS context means I didn't follow my own rules and put a scale on this map. So else you would have known how big it is. Anyway, so mapping inundation. I guess maybe this slide's also got too many words. We've sort of seen this logic before. Each stream reach has a water depth. Each stream reach has an identifier. Each grid cell has the identifier of the stream reach it connects to and the height above nearest stream or drainage, HD, and then you evaluate the inundation by this rule that I stated before. If the depth of the water is greater than the depth of the height above the drainage, then inundation depth is that, otherwise it's zero. So you can think of it in terms of this sort of set of rasters. On the left, I've got the reach and watershed IDs expressed in rasters. So the blue grid cells, number 111, number 222, number 333, and so on, would represent stream reaches. Then you've got the watersheds that drain to them, represented again by these numbers 1s, 2s, and 3s. So you can see all of these grid cells here drain to that reach, all of those grid cells drain to that reach, and so on. Then on the right, I've got the height above nearest drainage. I've also got the watersheds sort of depicted with these polygons around the grid cells. And now the numerical values represent, and this is sort of hypothetical numbers that I made up to sort of try and illustrate this point, the height above the drainage of these grid cells. Then we say have maybe the flood stage in each reach. So the depth of water in reach 1 said is 3.5. The depth of water in reach 2 is 2.5. The depth of water in reach 3 is 1.5. So then we look at all of the grid cells in reach 3, and because this depth is 1.5, all of the ones that are less than 1.5 are flooded. So you should see that colored in the light blue is the grid cells with a value of less than 1.5. So that would be the extent of the flooding in this watershed. In the adjacent watershed that drains to this reach, the depth of water I said was 2.5. So the 1s and the 2s are flooded, but the 3 is not flooded. So you get an situation here. We've got two grid cells that are adjacent to each other. This one is 2 units above the stream. This one is also 2 units above the stream, but because this one is in a drainage which has a different inundation depth, this one doesn't get flooded and the one on the left does. So we're effectively doing the mapping by catchment. That's the basic model element we're choosing. We can make the catchments as small as we like or as big as we like, but we're doing it with catchments. We're not doing it on a sort of individual cell by cell basis in terms of the height above the stream modeling and in terms of the depth of water modeling. So go ahead. Question here.
They are all integers. We don't have partially flooded cell.
We don't. So the question was, do we have partially flooded cells or not? And the answer is no. Well, I mean, that's separate from these numbers being integers. I was just using integer numbers for simplicity. You can certainly have the height above the stream could be 1.2 or 2.4, and we'd apply the same rules. With this model, we have a single elevation for each grid cell. Therefore, it has a single height above the stream that we've calculated. And we're saying if the water depth exceeds that, it gets flooded, the whole grid cell. If it doesn't exceed that, that whole grid cell doesn't. So we're basically doing our calculations at the scale of the grid cells. And that's a limitation. Maybe if the grid cells are large, you've got inaccuracies. So this work will get better as we work with smaller and smaller grid cells. I mean, that happens a lot of times with GIS. If you get smaller and smaller grid cells, you can get more precise results, but you have to do a whole lot more computation.
Let me put some perspective on this. So we've just been working with LiDAR on these catchments. The average area is, let's say, 3 square kilometres. We're now working with 1 metre LiDAR data. 1 metre LiDAR data in 3 square kilometres translates to 3 million cells in a catchment, 3 million. So yes, I mean, maybe the cell's not partially flooded, but you got 3 million of them. And in fact, the number's almost overwhelming. Actually, the degree of detail is just incredible compared with the size of the units that we're dealing with for the hydrology.
So it's important to actually calculate the height above the stream and get the stream nicely mapped. And you get some complications when you're working with vector stream networks that perhaps are inconsistent with the digital elevation model. So what I've got depicted here is a vector representation of the stream and also a raster representation of the D8 flow directions calculated using the rules that we have for D8 following the direction of steepest slope. So you've got these flow directions, and the streams that we're using in the approach that we were working with the National Water Model starts each stream at the channel head of a NHD medium resolution stream, because we're mapping streams at that resolution, and effectively traces them down. So it works with a different representation of the stream than is given by the NHD stream. The NHD stream is this one on the top, this blue line here, and you see it's not exactly in the valley, and we would start our stream here and it would move down and follow the valley. I've also got shown there the high resolution NHD stream that starts there and actually continues up. So there's a question of resolution as well. So zooming that out a little bit, here you can see the black line is the NHD medium resolution stream, and you can see sometimes it doesn't follow down the valleys directly. If you want to calculate the height above the drainage, and you're working with this DEM represented by these contours, then you really need the streams to be mapped in these valleys. So that's why we actually use an approach that calculates digital elevation model derived streams starting from each channel head, rather than using a straight rasterization of the NHD streams, which would in certain cases miss the DEM valleys. So this is what you get for that particular example, and I've just colored in dark blue 0 to 2 meters, 2 to 5 meters for the lighter blue. You also get some problems sometimes, and this is a particular place in Onion Creek where if you've mapped the channel network using the approach that you've learned, fill the sinks, calculate flow directions, it turns out that there's a railway line with a bridge that goes over this little creek, and the pit filling fills up this whole area behind it, and the stream that's delineated using the methods you do actually takes a long detour up here till it can get across the railway line there, and then it flows back. So there's a challenge in terms of mapping that. If you look at the NHD plus stream, it's also sort of deviating a little bit. It's not following right in the valleys, but it sort of follows the direction that goes underneath the valleys. So we've been effectively working on ways to sort of automatically resolve these things over large areas. I mean, you can always resolve it manually. You can say, oh, well, I'll look at it. It's obviously problematic, but you're dealing with thousands and thousands of these things over large areas that you have to work with. So there is the railway barrier that the fill DEM deflects. So what we've developed is what I'm calling a soft burn-in or etching approach using high-resolution streams. So the high-resolution streams from the National Hydrography data set are these shown in blue with these arrows showing their flow directions. and we basically take an approach where we trace down these flow directions, and we don't allow the elevation to go up along them. If the elevation goes up, we lower it down, and you effectively drill a little pathway following the high-resolution stream through the DEM. And that cuts a little nick through through that location there and lets you get a better representation of the stream network and then of hand. So here's an illustration of basically how that works. There is the hill shade of the DEM, and there's the sort of blockage that's really artificial because water can flow under there. The NHD high-resolution streamline is following that path. So if we follow that path, you can see there's a 51 and a 43, but there was a 40. So tracing along this path, you go 41, 40, and then you lower that to a 40, you lower that to a 40, and then it goes down to a 39. So you end up with a digital elevation model that's got the hole punched in it. And let me skip that. And you get you get this result. So here would be the hand inundation for the 10-meter DEM with the obstacles removed using NHD high resolution, whereas previously you would get this sort of effect.
How would that method differentiate between like a railroad bridge versus an impoundment or a culvert or something like that? Something the water maybe can't read.
So it wouldn't really. It would assume that it basically forces water to follow downhill along where a stream has been represented. So if there's an impoundment, oftentimes the impoundment would probably be represented by a flat surface at the top, and if it then is a sort of a little lip where there's the dam wall, assuming the DEM's high enough resolution to represent that, it's going to cut a notch through wherever the stream happens to be drawn on the map. That may or may not be ideal. I mean, we're dealing with sort of really small-scale problems. We're trying to automate them over a large area, and we're saying that the information given to us by the blue line that somebody's given us on a map is better than what you get out of a DEM.
Can I make a comment here, David? So we made some studies about this here. When we started developing the hand method, we started to make some experiments about what it would take to do this for the whole country. And it was if we could do a flood anywhere in the United States. And clearly there's lots of places that have lakes. I mean, there's Lake Travis, for example. It's already wet. We're not going to say anything about the fact that Lake Travis is a lake. Likewise, near the coast, there's lots of swamps where there's a lot of water there already. And so what we did to deal with that was to go through and do this analysis like what we're seeing here and create the map as the methods that we're describing here show, and then we subtracted from that all of the areas that were permanently mapped as water bodies. So there are mapped water bodies in the National Hydrography dataset, and by that we differentiated out the part of the water that's there all the time and the additional amount that's there when the flood's passing through and the levels are higher than normal. And that way, otherwise when you go down near the coast, for example, you suddenly find, oh my gosh, we've got water everywhere. Well, it's an artificial thing to say that. And so that's basically, we used another GIS data set, which was the boundaries of the impoundments or the existing water bodies as a mark of permanent water. And what we were doing here is to get inundation for water that's only there during flooded periods, which is in excess of that.
Okay, thanks. So that's actually one of the strengths of GIS. It effectively allows you to really easily combine information from multiple sources that have a sort of geospatial construct to them. And you've got information about lakes from one source, you've got information about height above the nearest streams from another source, and you're developing the capability to, based on their location, consider and deduce what's going on at any particular place. So that's a sort of an enabling feature that sort of has cropped up throughout this class. I skipped over this slide with the Gory details. This goes into the sort of method used in terms of doing this etching in, rasterizing the NHD plus streams, lowering the elevation of the streams, removing the pits, deriving the flow directions, keeping the D8 flow directions only on the grid cells, and then that actually motivated development of a new TAUDEM function called flow direction conditioning that effectively implemented given a set of flow directions and given a DEM, condition the DEM to be compliant with those flow directions following these methods. So that's also to, again, motivate the idea that as you're working in a sort of a GIS concept, sometimes you need to sort of invent your own methods for doing things because your run-of-the-mill sort of off-the-shelf system hasn't anticipated exactly what you want to do, but the programming capability of working with the data sets and knowing how they work lets you be quite creative. So this shows some of the adjustment that happened. So this was the difference between the original DEM and the flow direction condition DEM, and you can see that the biggest differences were right at that railway crossing. There were other differences scattered around all along the streams. So this last bit here, or the second to last bit, is using hand to determine stream reach hydraulic properties. This is a real interesting idea. You start from these stream reaches, and we're really interested in, okay, so what are the hydraulic properties that we need? So we can think of, there's a table here that's waiting to get filled in, where each stream reach has a unique identifier and the depth of flow that's going to be in it. And here you can think of, this is the idea that Dr. Mann was trying to describe earlier, where you're cutting the terrain horizontally rather than with vertical cross sections. You have the entire prism that's represented by a channel, and you've got a water surface that's at a fixed height above the bed of the channel, the fixed hand value. And then if you've got that, you can calculate by counting how many grid cells are in this prism. You can calculate the surface area. You can actually count the number of grid cells and the depth of them to get the volume. And then you get an average cross-sectional area as the volume divided, well, as the average cross-sectional area is the volume divided by the length of the channel. You can get a wetted perimeter as the bed area divided by the length, the top width as the surface area divided by the length. So these are sort of reach average properties that sort of, this is the reach averaging approach rather than the channel cross-section approach, and hydraulic radius as the cross-sectional area divided by the wetted perimeter. So these are some of the quantities that you then need to do hydraulic calculations and routing downstreams. So this slide goes into the sort of methods for that. For each catchment, for each height, you identify where the height above the drainage is less than the height you're evaluating. You've got the area of a single cell. You get the surface area as the sum of all of the cells that are inundated. You get the bed area with the surface areas of each individual cell. So now each grid cell has a slope to it, so you can actually work out the surface area of a sloping grid cell can be calculated as, and this is derived based on sort of Pythagoras. If you think there's a slope, you can get a horizontal length 1, the vertical length is the horizontal length times the slope, and you take that squared plus that squared, you get the square root of diagonal length, and that gives you the sort of surface area, which gives you an approximation of bed area approximating each cell as a sloping plane. Then you can calculate the volume based on the heights minus the height above the drainage, and then apply these calculations. For this to really work well, the topography should represent the bed elevations. Oftentimes it does not, so to the degree that the DEM is representing the water surface rather than the bed, you've got an approximation, and that's going to motivate the need for us to actually combine bathymetry information with our surface DEM data, because using bathymetry you're going to get a better result. Now if you're dealing with a river that's empty a lot of the time and you've done the mapping when it's empty, and then when a big flood comes down, maybe the little bit of water that was there is insignificant compared to the flood. So for large floods, I think it will improve a little bit in accuracy, but when you've got low flows, you may have some inaccuracy come in because of that. So this is an example of sort of doing some of these calculations. So here I've isolated catchments, and I've applied different height values. So with a height of 1, you can use the sort of raster, you can use the raster calculator to identify all of the grid cells for which the hand value is less than 1, and you can then calculate the surface area. You can calculate the hand value, or the depth value minus the hand value averaged over those grid cells to get the volume. You can get the bed area, calculate the length. The length you actually have to get independently, looking at the sort of horizontal length along the stream channels. And then you can apply the formula that I showed on the previous slide to get the area, the perimeter, the top width, and hydraulic radius. So in the exercise, we'll actually have you do this a couple of times manually for one single catchment to get a sense of how that works. Now it's been programmatically applied over all of the catchments across the country. So the sort of thing that you get out of this are things like where you've got hydraulic radius as a function of height, weighted perimeter as a function of height, top width, and area. And those are what you need for effectively applying rating curves. So this is an example for Eanes Creek, which is a watershed somewhere near and dear to Dr. Madman's location in his heart. I guess he was the city, you were the city engineer there or something?
I was the drainage engineer, yes.
Drainage engineer,
Yes,
okay.
I approved all the new commercial buildings and subdivisions for compliance with the city's drainage ordinances. And in fact, there was only one ordinance which said the full effect of development on runoff shall be accounted for. Okay, there's your legal basis. Then people come in and say, I want to get a permit. So I've got to connect the full effect of development on runoff shall be accounted for with some technical process to make judgments about whether this building should be there or not. And I did it for that creek. It was called Dry Creek at the time. This was when I was an assistant professor. There was a big flood on this creek in 1981, and we found just at the point where it just turns up there, that big upward kink there was a strip mall there. And the water came up to about the elevation of that clock inside the strip mall, and it rose so fast inside that there were people in a Chinese restaurant that had to push open the door and let the restaurant fill up before they could actually get the door open enough to get out of the restaurant. It happened about 9:30 on a Sunday night. And so after that, the city decided they needed some regulation, and so I was their drainage engineer. And this was all before, years and years beforehand, and National Water Model and all that. But I worried about just that one creek. It was an instructive exercise. I won't go into more war stories, but suffice it to say, we had some floods. It wasn't. So
there is Eanes Creek, and here's the sort of result that you can get. Cross-sectional area is a function of depth. Hydraulic radius is a function of depth, and then you make an assumption of uniform flow. So the hand approach is simplifying the hydraulics from perhaps if you solve the Saint-Venant equations. And then you've got Manning's equation, which here calculates based on discharge and Manning's roughness, the cross-sectional area, the hydraulic radius, and the slope. So really you can think of solving for the cross-sectional area given discharge, and then depending on where you are in the cross-sectional area curve, you can get the associated depth. And that gives you the stage height versus discharge, which is the rating curve. You have to come up with numbers for the slope. That can be obtained from the DEM, the elevation at the beginning and the elevation at the end. We've emphasized slope quite a lot in this class, so you should be solid on that. Manning's roughness is, again, you'd need a quantity that knows something about what that stream is, what's its stream bed, things like that. In the National Water Model, it's hard to get that information, and I think there's just a fixed value that's that's used, but that's an area where there could be improvement. So then once you've got a forecast discharge from the National Water Model, you can look up the flood depth, and then you can use hand to map the inundation. So sort of an interesting innovation in this work is that the hand is not only used for mapping where flood inundation occurs, it's also used for deriving the hydraulic properties of the rivers that we are working with. So that was the second to last point here. So there's some of the other considerations. So now I'm going to get a little bit perhaps philosophical and talk about some of the bigger picture ideas related to this. This slide shows that this whole procedure has been effectively automated for the Texas flood response approach. And this slide was obviously from Dr. Maidment, and I've put that on some of the slides, but didn't remember to put it on this one. So the National Water Model discharges go to converge to depth using rating curves. Then you have the inundation mapping that's used for disaster districts. And ESRI is involved in part of it. National Water Model is involved in part of it. GISWR is a big water information system company that's helping with this as well. Then we wanted to apply this over the whole country, so went to some colleagues at University of Illinois at the National Center for Supercomputing Analysis, where there's this Rogers supercomputer, which sadly has been decommissioned now, but at the time it was working, effectively implemented this process that goes through using the NHD plus flow lines, the high resolution flow lines, the 10-meter digital elevation model, going through all the sort of D8 flow directions, D-infinity flow directions, and ending up with a hand raster to effectively provide a result over the whole country that can be used, and in fact is being used in the National Water Model. And you can go to this website at TAC, and I hope that's the current one, but if it's not, I'll have to fix it. And get this data for any area in the continental US you might be interested in. One of the other ideas about this is that we spoke about calculating the hydraulic properties for individual catchments in reaches. So that actually makes this a local calculation. So you can think of once you're doing those sort of reach and catchment level calculations, you can split the terrain apart. You could actually send each one to a separate processor, so that becomes very amenable to parallel processing. You can also possibly use high resolution data in places where you have it. So if you organize yourself over the whole country, and then you said, okay, well, Texas is flash flood alley. We really need to worry about that. Let's get all the high resolution LiDAR data we have. Utah, we're not so much subject to this sort of flooding, so it really isn't worth the money to perhaps map with LiDAR data, at least for that purpose. There's a lot of people here would love to have LiDAR for other purposes, perhaps fish habitat and the like. But you can you can incrementally refine the digital elevation model just for a singular catchment and sort of get incremental improvements. So you can exploit high resolution data where it's critical. So this is a slide from Jing Zheng that shows the sort of increasing use of LiDAR. And you can see the moving up to real high resolutions, and this is the railway crossing that we showed previously in Onion Creek, where there's better approaches to mapping the flow across that using LiDAR data. The idea that you might want to integrate topography with the bathymetry. So here we've got high resolution topography from LiDAR. If there was bathymetry data, if you could get sort of blend that in with the single data set, your reach scale hydraulic property calculations that assume the digital elevation model represents the bed are going to get better. There's also we need to think about what's happening with the National Water Model. So we saw this slide earlier when Dr. Maidment was presenting the National Water Model, that goes from weather model forecasts to weather predictions and of precipitation and runoff from this hydrology model. Then that runoff needs to get routed down the channels. Right now, that routing down the channels is using Rapide, which is doing a sort of Muskingum routing, assuming channel properties. It doesn't use the actual hydraulic properties that we're calculating from hand. It's made other assumptions that were much coarser about the channels. So that routing is actually affecting the magnitude of discharges that we're getting out in these forecasts. Because if water is coming off the catchment slowly, it tends to spread out. If it's coming off the catchments quickly and aggregating quickly, you get peaks. I think there's an opportunity to improve that routing using the hand-derived channel hydraulic properties, and that involves sort of additional hydraulic routing models, and there's quite a bit of research going on in that area as well. So the routing could be improved based on that. There's also a question of the stream segmentation. So what the approach was that we first took was using the NHD catchments and effectively deriving a hand rating curve for each catchment, looking at the flow through that and applying it like that. But they weren't really designed with hand hydraulic properties in mind. They were designed with just a convenient way to subdivide the landscape. And the suggestion has been made, and this is again also work with Jing Jiang, that a more uniform segmentation may be better. So here for Onion Creek, he's illustrated a breaking of the area into sort of more uniformly delineated stream lengths and uniformly delineated catchments. And the suggestion is that this then would give you a better mapping of flood inundation. So that's another improvement to consider. So some of the summary points, and golly, this slide really breaks the rules on too many words on the slide, doesn't it? So hand is a special case of tau-dim distance down. The hand approach suggests a way to rapidly approximate real-time flood inundation. I'm saying approximate because it's not solving the sort of full two-dimensional shallow water equations over the surface that some sophisticated models will do. But I would submit that it's often just as good because the information needed to really get the benefit out of those models is often challenging to get. It supports flood inundation mapping where the data to support hydraulic calculations is limited. It neglects some of the details of river hydraulics. Again, the information is hard to get. It includes an approach to approximate the reach scale hydraulic properties, really acknowledging that all of these things are approximations. We need to think about what the best reach length is. It's premised on good digital elevation data and a consistent stream raster. The topography should represent the riverbed elevations. And there's research to sort of reconcile the elevation and the hydrography. The obstacle removal approach that we're using is it's sort of expedient, but it's not necessarily the most ideal approach, even though it took me to developing a new flow direction conditioning approach for tau-dim. Having a consistent elevation and hydrography is something that the USGS is taking on more seriously and addressing more holistically in their 3D elevation program. It was calculated across the whole US with the 10-meter resolution DEM, and it could use high-resolution LiDAR data where it's available. So got here some, if you want to learn more, there's all of these papers listed here. That this idea actually dates back to 2005, were the first papers that sort of started articulating using a DEM to calculate height above stream and use it for flooding. Then the paper with myself and Teklu looking at the proximity measures, and Nobre, who's a researcher from Brazil, has done quite a lot of work on this idea, and he was the person who coined the word hand. And then we've got some papers just out on the sort of methods that I've described in the Journal of American Water Resources Association. So let's see if there's any questions, if there's time.
Okay. Ready to declare victory? Okay, great.
Certainly.
We'll see you next Thursday here in Austin, David. Thank you.
Good. Good.